It's a tough job. There's a lot to know, and I hope that through tonight and what we've presented in the past, that I hope it helps educate. Again, Scott McDonald from Avenue Renewables. And again, thank you all for all the hard work you've done. I echo everything that you've heard here. It is a hard job, and we are very appreciative of that. We've hired two internationally recognized experts that have helped us in sound and health with the design of our wind plant here in Parishville and also Hopkinton. We have Rob O'Neal from Ollison Associates and also Dr. Chris Ollison of Health Management. Both of these gentlemen have been involved in numerous hearings and tribunals along the idea of testifying along these topics, and both are recognized as independent experts in their field. So what we'd like to do is start out with Rob. He's going to present on sound, and then we're going to move to Chris, who will present on health.
And are we going to be able to ask them questions?
That's up to...
I think we need to.
Yes. I'd like to give these people the courtesy of listening to them and not interrupt them. After that, I'm sure we're going to have questions, and like I said, we're doing work, and these decisions are based on facts, so it's a good time to ask these questions, okay? After the presentation, so if we give them the courtesy of giving their presentation, they have to concentrate. I don't want to send them off track.
That's fine, thank you.
Okay.
I don't know if you want to, if those lights, maybe one more lights might help. It might be a little tough to see the screen, if that's possible.
Yes.
These right here, maybe?
There we go.
All right, I'll speak up in a microphone. Hopefully people can hear me. Again, my name is Rob O'Neal from Ollison Associates. Thank you to the board and other town officials for allowing us a chance to come and hopefully just share some of what we know, our experience between sound and health, and how that can apply to wind turbines. As Scott said, I'm going to talk about sound. I've got, as you can probably tell from the gray hair here, I've got a lot of years experience doing this, 30 years of doing community sound. The last 13 specifically dealing with wind turbines and how sound from wind turbines goes. I have a couple of national certifications. I'm board certified by the Institute of Pollution Control Engineers, and I also am certified by the American Meteorological Society, the AMS, in meteorology. I've testified before, a lot of experience doing this. I spent a lot of, this is not to show necessarily what we do, but the point is, I spent a lot of hours, days, weeks, over the last 13 years at operating wind turbines. So I really feel like I do understand sound, how it operates, how it works. And I'll try to bring some of that experience to bear tonight. I'm going to talk about just a quick sound 101. I don't want to bore people too much with that, just a couple of basic things about sound. Then talk a little bit about monitoring, how to measure sound, about modeling, how we try to predict the sound. I'll touch on low frequency and infrasound, that's often a topic, questions come about that. And then finish off with some noise design goals. Sound is just the movement of air. It's sound waves going through the air, it's vibration of air. We measure sound with a sound pressure level. Our sound meters pick that up on a little microphone. It has a diaphragm. We're measuring sound pressure. That's about as detailed as I want to get on that. The human ear hears a wide variation of sound levels, from very quiet to very loud. That's why we use the decibel scale to rank them. For example, the conversation in this room right now, if I had my sound meter, by the laptop there, general conversation before the meeting started right now is probably around 60 decibels, just for perspective. Decibel addition, again, because it's logarithmic, if you take a source of sound that's 30 decibels, and you choose a second source of sound that's also 30 decibels, it's not 60 decibels. It's that logarithmic math, so 30 plus 30 is 33 decibels. This hypothetical example shows you here. That's sinking for a second. On the other hand, if you have a source of sound that's 30 and a second source of sound that's 40 or more, the higher source of sound will then predominate. 30 plus 40 is not 70, 30 plus 40 is essentially 40, it's 40.1, something like that. It really rounds to 40, so the louder source will predominate or dominate. We have two sources that vary by 10 decibels or more. Again, it's basic decibel logarithmic math. But it's an important concept, because sometimes people do get confused and they think of, you know, if it's 40 today and you're going to bring a new sound in like a turbine that's 40 decibels, now it's going to be 80 decibels. That's not true. This graph here is just, there's a lot of detail here, but the point is sound is composed of, as I said, vibrations of the air, and they can vibrate at different frequencies. We have, all the way from infrasound, low frequency, middle and high frequencies. This chart here is a chart of 1/3 octave bands. By definition, the sound waves are different frequencies and different octave bands, from that low bass you might have in your stereo to the higher frequencies. We hear best in the middle frequencies here, around 1,000 hertz. I'll show you another slide about that. I'll talk more about infrasound and low frequency in a few more slides. Okay? But the other point of this graph is, besides the scale here, you see 0 to 120 decibels. The lower you get in the octave bands, as you get into the low frequency and infrasound, the higher and higher the decibel level has to be for us to hear it. We don't hear low frequencies well at all. We hear the middle and high frequencies well. We don't hear low frequencies. So, for example, to hear a sound at 10 hertz, it would have to be around 100 decibels loud in that frequency for a typical person to hear it. Obviously, there's a little play on either side of that, but the point is, to hear it, it's going to be very loud at those frequencies.
Can you stand on the other side of that so we can see it back here? This whole side probably can't see that part.
Yes, you stand this
Is
side.
that okay with you folks?
Yeah.
Oh, yeah.
Okay, sure. Sorry about that. So this graph here is similar in terms of the x-axis. Again, it's showing the frequency on the bottom here. Again, high frequency here, middle frequency, here's 1,000 hertz here, and then 10 hertz down here. So kind of get into low frequency and infrasound that region. What we hear talked about a lot is A-weighted, 35 dBA, 40 dBA, 45 dBA. And that A-weighted and a dBA is the A-weighted filter. That's set by a standard. This is a national, international standard that everybody uses. All the equipment is used. There's no deviation from this. This is an A-weighted filter, if you will. So the point of this is that we hear very well at 1,000 hertz, and these frequencies up here. So there's no adjustment. There's zero adjustment there for the sound level you measure at 1,000 hertz. That is as is. We don't hear so well on the lower frequencies, so that's why the filter drops off. So, by the time you get to 10 hertz, you're not going to hear anything down there. Our ears don't hear that well at all. And that's the point of this filtering. Again, I'm not going to get into too much more math on that. Just trying to broad concepts here. We don't hear low frequencies, we hear middle frequencies, and that's why the A-weighted scale has been universally adopted to describe sound to people and sound levels. All right, switching to actually measuring sound. There's a couple of photographs from some field work we've done over the years. We measure sound. There's a couple different instruments that we use. This is one of them right here. This is a Norsonic. You put a windscreen on it to reduce the sound of the wind itself over the microphone. And these instruments are very sophisticated. They measure the microphone. They measure whatever sound it picks up. Doesn't discriminate. Measures everything. It measures the A-weighted, the infrasound, the low frequency. All the different frequencies are measured. When we do work, especially for any wind project, we also measure the wind down at ground level, basically the same height as the microphone, more or less. because the wind and the wind speed is very important in understanding sound levels. As the wind speed at the ground increases, then the sound levels also increase. So we use that pretty routinely for our measurements. What I'm showing you here is it wasn't done by me. It's in one of the reference books, but it's a pretty fair example, I think, of what you're going to find in a rural agricultural type of community. So this is a 2-week measurement period. So this x-axis on the bottom spans 2 weeks, and the y-axis over there are the decibel levels from 0 to 70 decibels. These are what's called the L90, which is basically the ambient background. That's the sound levels that are basically filtered out all those sort of intermediate events. This is sort of the steady state quietest background. And the takeaway from this is there's a range here of about 17 decibels to 54 decibels of the quietest levels in a community over about 2 weeks. The sound changes all the time. It's not a steady number unless you happen to put your meter, next to a compressor or something that's running for 24 hours a day. But that aside, if you're taking typical community measurements, you're going to see a variation something like this. It's going to vary up and down. And the other piece there is the wind speed. So the consultant that did this plotted the wind speed. This ground level wind speed is over this axis here. And not surprisingly, when it's really windy, it can be really noisy. Not always necessarily, but you can have sound levels that are loud from other sources as well. But there's a pretty decent correlation between the ground level wind speed and sound levels. Even the quietest sound levels can be over 50 decibels in a rural agricultural community.
Where is that from?
I don't know where it was taken. I got it from a reference book. All they said is it's a rural community. All right. Predicting the sound levels. How do people do that? So there is a. I've highlighted here in kind of bullet form some of the key elements of the sound prediction process. You want to start with some type of standard. What's mostly used is the ISO 9613 propagation standard that has a set of rules and equations in there to basically take sound from a source and calculate that out into the community. And as part of that, of course, you need the project layout. You need to know where the wind turbines are. You need to know where the homes are. So all that stuff goes in from GIS information. You put that into a model. Terrain data, if there's any terrain, you put that into the model. They can incorporate elevation. What's routinely done is this is really for kind of understanding the short-term worst-case sound levels. You're going to take the information from the sound level manufacturer, whether it's GE or Vestas or any of the turbine makers. They provide, by standard, some data sheets of sound levels as a function of wind speed, and it's in sound power, but it's basically sound pressure. And that's from cutting wind speed, which is usually around 3 or 4 meters per second, up to cut-out wind speed, which is usually around 25 meters per second. And the sound levels will increase with wind speed up to a certain point, usually around maybe 9 or 10 meters per second. And then after that, even when the winds continue to increase, the sound levels from the turbines per se do not increase anymore. That curve flattens out. And that's been proven over and over again in real life. So we take the maximum sound level, whatever that worst case is, we take that, we assume that every turbine is emitting that at the same time. Obviously, whatever the turbine height is, that's put into the model. Meteorological conditions go in. What's typically used is temperature and relative humidity conditions that absorb the least amount of sound, therefore will generate the relatively highest sound levels. That's a conservative assumption. The 9613 standard assumes a moderate ground level inversion already exists. So it's an inversion, of course, is where the temperature gets warmer as you go up, so that helps to refract and propagate the sound downward. Obviously, sound drops off with distance. And the other takeaway is that in this standard, the wind is always blowing from the turbine to wherever your calculation point is, a home, church, school, whatever it is. I'll show you a graph of that in a minute. So this is kind of, these are a lot of your inputs to the model. This graph here shows an example of what typical model output will look like. This is for a project from many years ago, but you can see here you've got your turbine arrays in the pink dots, and the blue squares. It's probably tough to see in the back, but these blue squares represent homes, and then you've got your color contours at different decibel levels. You're going to have a map, something like this, which is going to show you from both a contour perspective what you can expect for worst case sound levels, and then there'll also be typically the model will produce output at every one of those specific points. Every one of these blue squares will produce the sound level as well. These two graphs kind of zoom in, different project, but it shows you, if you just look at a single wind turbine, it's sort of like dropping the pebble in the pond. Because the model assumes that the wind is blowing in every single direction uniformly, even though that's a physical impossibility, that's why all the circles are uniform, because it's blowing outward uniformly, worst case. Once you start putting a bunch of turbines, in some kind of array or alignment, then that still happens, but as you get further away, now the contributions from each turbine are adding together, and you no longer have quite that concentric circle pattern. But each turbine is putting out the maximum sound power level, and it's all uniformly radiating outward. So just two very simplistic examples of how the propagation modeling works. And those will give you the relatively short-term worst-case sound levels. A second type of analysis that's becoming required, especially here in New York State, is what would a long-term analysis look like? In other words, what if you looked at the conditions over a year? So, well, the big thing is, what is the wind speed at hub height over the course of a year? Again, this is not for this particular site or area even. This is another older example from a sample site. But this shows you there's 8,760 hours in a year. So there's 8,760 wind speeds here at a hub height. I think this was 100, 110 meters above the ground. So the takeaway from this message is, here's wind speed from 0 up to 18 meters per second, and the wind speed varies up and down over the course of a year. Not surprising, right? That's probably not real news to anybody, but it's not blowing at 20 meters per second every day, every hour of the year. So again, this is another hypothetical example, but if you had 8,760 hours from January 1st to December 31st here, and you took that wind speed and you match it up with the sound power level from the turbine manufacturer, because we know what the sound levels are from the turbine at every different wind speed, you can then kind of come up with a graph similar to this, where obviously there's hours during the year where the wind is below the cut-in speed, so the turbines don't operate. So the sound level is 0 from the turbines. That's what this